Okay, welcome to the next talk in HoTT-UF 2020. I'll just remind you that we're keeping questions to a minimum during the talk because we want the speakers to be able to end on time. So the talk will be roughly 20 minutes with about 5 minutes for questions afterwards. So this talk is by Eric Faber, and the title is Effective Conv Fibrations in Simplicial Sets. Please go ahead.
Thank you, and thanks to the organizers. I think this is all going wonderfully, and also thank you for giving me the opportunity to speak. So I'll be talking about work that I've been doing for the past year together with Benno van den Berg. And to give this a bit of an introduction, oh wait, there we go. Let's look at a timeline about this subject. So wait, I should say that the title of my talk, Effective Conv Fibrations in Simplicial Sets. Why are we interested in that? So in 2012, the first model of homotopy type theory was announced, and it was actually a simplicial model, which was the first proof of concept that homotopy type theory is workable, it works, and it's a language of abstract homotopy theory. So people were quite happy about that. But to fully leverage this connection, everybody knows that you want to work with a constructive model to really lay the connection between computation and homotopy. But then in 2013, a counter model was produced, which shows that if you do the naive thing and you work with ordinary Conv fibrations, then there are non-classical situations where this will fail. And that was a Kripke counter model produced by Coquin, Besem, and Harman. After that, people started looking at different places to look for this constructive model of homotopy type theory, in something that we can maybe summarize as the cubical turn. I stole that from my co-author. And following years, there was a lot of subsequent research on cubical sets. Some of that has trickled down back to simplicial sets, for instance, the work by Gambino and Zattler. But there remain some open questions. So why do we want to look at simplicial sets again? So it's not a coincidence that the first model was in simplicial sets, because in some sense it was the category that people were most interested in. If it works there, then we really have something nice. But on top of that, there are also some negative results for cubical sets, both in the homotopy domain and in the logical domain. So it is still of everyone's interest to produce a constructive model of homotopy type theory in simplicial sets. And why is that so hard? So I've tried to summarize this in this triangle, where one could say, okay, ideally we want to have all three corners of the triangle. We want to have something which is called local, and I'll go a bit into that at the end, perhaps. We want it to be simplicial, as I said, and we want it to be a constructive model. And I think any pair of these have been given some sort of answer. So the first model by Kapuk and Lumsdain and Vovodsky is this edge. Cubical world is this edge. And this is the work by Gambino and Zattler, where some of the advances in cubical sets have actually been translated back to simplicial sets. But to get all three corners of the triangle, something new must be done, and that's what the counter model has shown, that you have to come up with a new approach. So where have we got? So me and Benno suggest a new approach that uses effective Conv fibrations. And our current state of affairs can be summarized as we have a constructive proof that effective Conv fibrations are closed on the push forward. And with that, we only have this particular aspect of dependent type theory, but it shows that we avoid the theoretical obstruction of of Bayesian and Cocon, so the Kripke counter model. So that's why it shows that we are heading in the right direction. We also have that our effective Kant fibrations are a local, we call that notion of fibrate structure, which is very desirable. It allows you to define a Hofmann-Streicher universe in a very straightforward way. So it's another ingredient that we want. So essentially we're heading towards a model where we have the three corners of the triangle, but we're not quite there yet. This is work in progress. And so I should mention that our effective Kant fibrations are the same as ordinary Kant fibration if we're allowed to use classical logic. Every effective Kant fibration is an ordinary Kant fibration, and the converse holds using some non-constructive axioms. Right. There is some other work that has been done on simplicial sets. So let me just mention that, as I already talked about Gambino and Sattler, there's more recent work actually trying to push ordinary Kant fibrations to their theoretical limit. And it turns out that not all hope is lost due to this counterexample. So I should definitely mention Henri and Gambino, Sattler, and Shumilo. Right. So for effective Kant fibrations, we have written a paper that consists of 2 parts. And the first part actually doesn't talk about simplicial sets at all. The first part is a continuation of work by Richard Garner and Benno van den Berg on fibrations or weak factorization systems, I should say factorization systems for categories with something called Moore structure. And we have built on that by strengthening their notion of Moore structure. It was called differently in their paper. And we have managed to construct algebraic weak factorization systems rather than just weak factorization systems. But it follows the same philosophy. And then the second part of our paper is the most new, because it shows that simplicial sets satisfies the strengthened setting that we do now. And for that, we actually need a radical different approach to the original paper. So we have to do 2 things. We have to first verify that simplicial sets satisfy the axioms of Moore structure, and then we have to study their properties a bit more carefully. Right, so what is Moore structure? I'll mostly talk about the first part, because without the first part, there's really no point about talking about the second part. But because of time, I'll keep the second part short, unfortunately. So what is a Moore structure? So E is just a category with finite limits, and a Moore structure is an endofunctor that constructs for every object an object of things we might call Moore paths in X. And a Moore path in the topological sense is a path equipped with a length. So it's not an ordinary homotopy path. It has something extra usually. It basically looks like this. We have, for every X, we have such an object MX. It looks like an internal category, and it is an internal category. We do write concatenation rather than composition for bureaucratic reasons. And there are things like, so a Moore path in X has a target, it has a source. There's a notion of trivial path and a notion of composition given by mu. And since, I should also say that this functor preserves pullbacks. And since every mx admits a canonical arrow to m of 1, that thing should be thought of as taking the underlying length of the path. So m1 is the object of path lengths. So in simplicial sets, that is some mysterious simplicial set. And we do demand more stuff to come with this. For one thing, M should be a comonad. So there is some gamma like this, and the co-unit is given by the source. And it satisfies a whole bunch of axioms that make it look a little bit like this. So what happens if I'm in some m of x and I have a path there, then gamma x of p should produce something in mmx, so a path of paths. And the source of that path of paths should be p, and the target should just be the trivial path on the target of p. And then there are some funny things, like the length of this path is actually the length of the path you started with. So it looks like you have p in these two directions, and you slowly contract it to the target. And for that, you need another thing, that this diagonal here has also length p, but it is constant with value y. And for that, you need this alpha, which behaves a bit like a strength for all the structure that is around. Right. And then there are many axioms, and I should emphasize that this adds a lot more axioms on top of the original paper by Vandenberg and Garner. They are a bit more complex as well. And one of them is the distributive law that looks like this. If I have a composition of path and I contract it using this gamma, then that should be the same thing as first contracting the p and doing nothing with q. So we put something constant there, and then contracting q. That's one of the new ingredients. And luckily, and curiously actually, that most examples from the original paper do carry over to the new setting. And these include topological spaces, where M of X is the space of topological Moore paths in X, groupoids, chain complexes, and simplicial sets. And these all even have symmetric Moore structure, and for the rest of the talk, I'll actually be mostly concerned with symmetric Moore structure. I will not define that. It has a lot of subtleties, but it makes the presentation a bit more streamlined. Okay. So the first theorem of the first part of the paper is that we can produce a factorization of any arrow f in this category E that has Moore structure. It looks like this. This is essentially the same idea as in the paper by Garner and Vandenberg. But now we can say that this can be completed to an algebraic weak factorization system in the sense of Burke and Garner. And an algebraic weak factorization system, for those not in the know, consists of a left class of maps and a right class of maps, but they're not actually just classes, they're two categories. The left one is a two category of co-algebras, and the right one is a category of algebras for the comonad, where the comonad is given by the functor which takes the left bit of your arrow, and the monad is given by the functor which takes the right bit. And they look a bit like this. So co-algebras are what we call hyperdeformation retracts, and they consist of monomorphisms which have a retraction or a cosection, such that if I first retract and then go back into B, then that is homotopic in some strong sense, given by all the structure we have around to the identity. And algebras are the same thing as something we call naive fibrations, which are fibrations in the sense everyone thinks of. So what it means is they come equipped with, so we have an arrow from y to x, and they come equipped with something that takes a path in x and takes something in y which lies above the target, and it constructs a path in y so it extends it to a path in y that lies completely above the underlying path in x. So that's what everyone thinks of as a fibration, and we call it a naive fibration. And then we actually need another algebraic weak factorization system on our category. And this slide has nothing to do with Moore structure. I'll just maybe go very briefly through it, because we also need a notion of cofibration, and a dominance is a way of doing cofibrations constructively. So it's a class of monomorphisms. Those will be your cofibrations, but we actually impose a lot more structure on it. In fact, it will also be a double category. So we just use the known fact that there is a class, a dominance, which is the left class of an algebraic weak factorization system on E, and we call its elements cofibrations. So the second part of the paper actually also needs to talk about why we have such a thing in simplicial sets. But think of them as monomorphisms. Right. So this slide is probably the most important one of the talk. So if you're going to remember one of them, it should be this one, because this is what defines effective fibrations. And for the definition, we combine the two algebraic weak factorization systems that exist. One comes from the Moore structure, and the other one comes from the dominance. So recall that algebras for the Moore structure we called HDRs, or hyperdeformation retracts. Those things actually form a Grothendieck fibration, so there's a notion of Cartesian morphism between them. And a mold square is a specific type of Cartesian morphisms between HDRs. So it goes from I prime to I, where the arrows on the left and right are cofibrations. So that's what a mold square is. And how does this define an effective confibration? Well, as follows. So for an arrow to be an effective confibration, it should come with a solution to every lifting problem against a mold square. So how does an arrow lift with respect to a square? And we know how it lifts with respect to an arrow. How does it do that with respect to a square? It's as follows. So a lifting problem looks like this now. On the left, we have this mold square, and we have arrows here as in the usual case, but we also have this diagonal H. And then we demand that there's a filler over here, F. And this actually should not be formulated in terms of existence. It should come as a structure, and we can formulate this as having a right lifting structure with respect to some triple category, whose xy squares are mold squares. So we define a triple category, and using that we can define exactly what it means to be an effective fibration. Due to time, I will not show the triple category, but it's not hard. The key to remember is that by using this triple category, the compatibility conditions between lifts are actually very elegant and straightforward. Right. So then the main theorem of the first part of this paper is that if we have a category with symmetric Moore structure, then, and I take the push forward of an effective fibration along a naive fibration, so that's a bit more general than you initially want, and that is again an effective fibration. and functorially so. I mean, everything is functorial. So effective fibrations are closed on the push forward. And with that conclusion, we are happy because we have shown that our algebraic refactorization system models dependent product types. Right. So let me briefly say, if I have some time, say something about how this looks in simplicial sets. So the Moore structure of simplicial sets looks a bit complicated. If everyone had wondered where in the proof of this push forward, where all the combinatorics of simplicial sets has gone, it's in this Moore structure. So the object of paths is something called the simplicial set of traversals. And a path in X, in a simplicial set X, looks a bit like this. So here on the left, we have an n-simplex in X. On the right, we have another n-simplex, and there's a path between them. And these are not just any phase maps, but they satisfy some combinatorics, like they walk down or they walk up. So it's not any phase maps, but there is a subtle combinatorics that actually turn traversals into a simplicial sets. But key to our new approach and to showing all the axioms, including difficult axioms like the distributive law, is a new approach to this functor, using the fact that it's actually the Moore-path functor on simplicial sets is a polynomial functor. That's a separate new result that makes it much easier to check the axioms than in the original paper. Right. And then once we verified everything in simplicial sets, we can look at what things actually boil down to. And it turns out that the mold squares in, so the effective fibrations in simplicial sets, which we now call effective confibrations, they are uniquely determined by a subclass of mold squares that we call horn squares. And they look like this. So we have a boundary inclusion here and a face inclusion here, where this is just a pullback along a degeneracy map. And if you're very quick, you can see that if you take the push out of this thing on top and you include it into this thing here, then you just get an ordinary Kant horn. And that shows that every effective Kant fibration is an ordinary fibration because you have lifts. The lifting condition is the same as the lifting condition with respect to this push out induced map. And therefore
I'll just have to get you to try to wrap up pretty quickly.
Yes, this is the last slide. And for this reason, for the reason we have reduced everything to horn squares, the resulting fiber structure is local. That's because these things are representable, basically, which allows you to define a universe, and we'll do that in subsequent work. Effective Kant fibrations are ordinary fibrations, and we can actually show that classically the reverse holds as well. Right, so let me finish with some references to some of the papers I mentioned. Thank you.
Okay, great, thanks. Sorry, I didn't realize you were right at the end there. So let's all silently applaud Eric.
Thanks.
Okay, and are there any questions? Oh, there is a question in the chat.
Well, I can't do that.
What is M1 in groupoids? So M1 is their space of lengths. What is it for groupoids? Right.
So in the groupoid case, and Benno will correct me if I'm wrong, the lengths are actually trivial. So the groupoid case is just you can show that it's an extension of the normal groupoid model. So that's one of the cases where you do not have this length coming in. Is that so? Yeah. But a simplicial set that doesn't work.
Okay, more questions? Okay, there's another one in the chat. You say that, this is Daniel Grayson, you say that with classical logic, fibrations are effective fibrations. Does this tell us something new about simplicial sets?
Well, yeah, I think this work does tell us many new things about simplicial sets. So yeah, the answer is yes.
Maybe you can say a bit
maybe,
more.
yeah. I mean, so you, for example, you had this result like that you had push forward also for along naive vibrations. I think that is maybe not something everyone
Right.
is aware of.
Yeah. So wait, where?
Yeah.
Yeah, for instance, well, yeah, okay, and to add on to that, something springs to mind that we're only talking about symmetric Moore structure here, and on simplicial sets, there's actually 3 types of Moore structure that you can distinguish, and in that sense, it shows a bit more of the different subtleties you can have in the definition of a Kant vibration. And another thing is that if you that our result of push forward actually says that if I push forward along a naive vibration, then I get an effective Kant vibration. And naive vibrations are more general than effective Kant vibrations. So in that sense, it's a stronger result for simplicial sets as well.
Okay, any final quick question? All right, well, if not, let's thank Eric again.
Thanks.
And now there's a half-hour break until the next talk.